Hello, I'm Yeon Kim and today I'm going to talk about the brachistochrone curve and the Euler-Lagrange equation. First of all, I'm going to introduce the brachistochrone problem and then I'm going to talk about the Euler-Lagrange equation, which leads us to the solution of the problem. Lastly, I'm going to explain about the cycloid, which is the answer of the problem. When I was in elementary school, I did an experiment with this apparatus to see which curve a ball rolling along is the first to arrive at its destination. The experiment led me to conclude that a ball rolling along a cycloid is the first to arrive at its destination. However, the experiment didn't give me enough explanation for the reason why the cycloid is the first to arrive at its destination. So in this talk, I'm going to show why the cycloid must be the fastest descending curve by using the method called the calculus of variations. So here's a problem. An object slides down a curve without friction, only under the influence of gravity, from one point A to another point B, which is lower than A, in the shortest amount of time. What should the curve look like? We call this problem the brachistochrone problem. So, what will be the answer of the brachistochrone problem? Intuitively, the answer to this problem looks like a straight line connecting A and B. Of course, this answer is not necessarily wrong. As long as the line segment AB is straight in the vertical direction, this answer is true. However, it is not a general answer because it has a limitation. So let's see what the general answer will be. Firstly, let's translate this problem to the coordinate plane. Let's take point A at the origin of the coordinate plane, and let's take the other point B as shown. Intuitively, gravity acts downward, so that's why we put the point B lower than the point A. And then we want to solve the problem for x. And the direction of gravity is downward, so we're going to rotate coordinate plane like this. So the x-axis goes there, and the y-axis goes here. Of course, if the curve connecting the points is called S, then ds can be expressed as follows. In the problem, there is no forces acting on the object other than gravity, and there is no friction, so the law of conservation of energy tells us the velocity at point P. If we substitute the velocity we found into ds and integrate, we get this. The value that satisfies the minimum value of this expression becomes the fastest descending curve. So how do we solve the problem? To find out, we first need to understand the Euler's Lagrange equation. Let's find big F, the function which is the integral of the function small f and has a stationary value. Here, the stationary value refers to the point on the graph of the function where the derivative becomes 0. If we express this mathematically, it would look like this. When small f is integrated from x1 to x2, if small f changes, the integrated value big F will naturally change as well. Considering this, the difference in change small f can be called delta f, and when delta f is integrated to 0, it can be said stationary. Thus, the following argument holds. Here, delta is called the variation, and the method of searching stationary values is called the calculus of variation. To better understand variation, let's draw a picture to check the difference between differentiation and variation, given that there are x and x plus ds. Differentiation is looking at the y values difference in one function, while variation is looking at the y values difference between the two functions by moving the function very slightly. If the variable that slightly moved y is called big Y, it can also be expressed like this. If we examine the differential and variational functions here, we can see that d over dx and delta are interchangeable. So if we put it like this, it will look like this. Earlier, we had the idea that the integral of delta f must be 0, so that it can be called as stationary. So if we substitute the result to the equation, it would look like this. If we partially integrate this here, it looks like this. As seen in the previous graph, the two curves have the same value at points P and Q, so the variation of the points will be 0. Therefore, delta f becomes this. Here, this integral must be 0 at any delta y, so the following equation holds. This equation is called Euler-Lagrange equation. Now that we understand the Euler-Lagrange equation, we can solve the Brachistochrone problem. If we put f, y derivative, x, in the equation we used when figuring out the problem earlier, we get this. Because of the Euler-Lagrange equation, it goes like this. Here, if we set the following term as c and express it for y derivative, dy is as follows. If we set x like this and differentiate both sides of the equation, we get dx. So, if we substitute dx to the expression of dy becomes this. So y is going to be like this, and big D is the constant of the integration of y, where if x is 0, then y must be 0. So D is going to be 0, so y is going to end up like this. But I've got point B in the first quadrant, so x and y is going to end up like this. If we plot this curve based on the x and y, we get something like this curve, which is called a cycloid. A cycloid is a trace left by the vertex of a circle when it is rolled over a straight line. Let's take a look at the equation of the cycloid. Let's say the center of the circle, C, and let the angle ACP be T. Also, let's let the coordinates of the point P be xy. The length of the line segment OA is equal to the distance the circle has been rolled, so OA is RT. Then we can let x as this and y as this. If we solve x and y for r and t, then they can be expressed as follows. This is the same answer we got when we solved the problem earlier, right? So we can say the solution to the Brachistochrone problem is a cycloid. These are the references I used for preparing the presentation. Thank you for listening.